Let's now discuss some properties of singular value decomposition. So let's say that we have a singular value decomposition, A equals U times sigma times V conjugate transpose. Again, U here has orthonormal columns. The diagonal of sigma is home to the singular values. The number of singular values is the rank of A, and the singular values, we order them in from greatest to smallest, and these are all positive numbers. And then V here also has orthonormal columns. What we're doing in this setup here is we're labeling the columns of U as U1 through UR, and labeling the rows of V conjugate transpose as V1 through VR. Well, it turns out that in this setup, that the columns of U and V are related to each other by the matrix A. If we take A and multiply it by the jth column of V, this always produces the jth singular value multiplied by the jth column of U. And if we take the conjugate transpose of A and multiply by the jth column of U, this always produces the jth singular value multiplied by the jth column of V. So these kind of look like the eigenvalue equations. However, this is completely different because our matrix here is not square, and then which allows U and V to be of different shapes. Moreover, if we have a singular value decomposition of A, we could take the conjugate transpose of everything in sight and obtain a singular value decomposition of A star. A star is V times sigma times U conjugate transpose. So we can see this with an example here. Here we have a singular value decomposition. A equals U times sigma times V conjugate transpose. Again, here there are two singular values, 5 and 3, which means that the rank of A is 2. Well, we just said that the columns of U and V are related to each other. If we take our matrix A and multiply by the first column of V, this should produce the first singular value of our matrix 5 multiplied by the first column of U. We also have a relationship if we transpose A, or conjugate transpose A, and multiply by the first column of U here, this should produce the first singular value 5 of the matrix multiplied by the first row of V conjugate transpose, or the first column of V. If we take our matrix A and multiply by the second column of V, this should produce the second singular value 3 multiplied by the second column of U. And finally, if we transpose A and multiply by the second column of U, this should produce the second singular value of our matrix multiplied by the second row of V conjugate transpose. So these equations are just illustrating the property that we previously mentioned. If we take A and multiply by the jth column of V, that is always equal to the jth singular value of our matrix multiplied by the jth column of U. And if we take A star and multiply by the jth column of U, that produces the jth singular value multiplied by the jth column of V. Our next property here deals with projection matrices. Let's say that we have our singular value decomposition, A equals U times sigma times V conjugate transpose. It turns out that the data in U and V can be used to extract projection matrices for each of the 4 fundamental subspaces. We can project onto the column space of A by taking U and multiplying by U star. We can project onto the column space of A star by taking V and multiplying by V star. And since we have orthogonality relations, we can take these formulas for the projection matrices onto the column space of A and the column space of A star and get projections onto the left null space and the null space. To project onto the null space of A star, we take the identity matrix and subtract U times U star. And to project onto the null space of our matrix, we take the identity matrix and subtract v times v star. So let's see that in an example here. Here we have our singular value decomposition, A equals U times sigma times V conjugate transpose. Let's say we wanted to project onto the column space of A star. Well, according to our formulas, we can do this by taking V and multiplying by V star. Remember, V has orthonormal columns, but here V is not square. So V star times V is the identity, but V times V star is not necessarily the identity. In fact, here what we find is that V times V star is exactly projection onto the column space of A star. So if you have singular value decomposition, you get projection onto the four fundamental subspaces with very little effort.